Hello everybody, I welcome you all again to Midas IT webinars, and the topic of today's webinar is the linear static analysis of a PSC Anchorage beam. Before I start, I would like to tell you something about Midas FEA. Midas FEA is an independent software. It is one of the software in the family of Midas IT software such as Midas Civil, Midas Gen, Midas FEA, Midas GTS. Midas FEA is generally used for detailed analysis. So the procedure is the global analysis, that is the moving load analysis or the static analysis, is done in Midas Civil, and for the detailed analysis of, let's say, anchorage blocks or the cable connection, is done with Midas FEA. First, I will take you through our general overview of Midas FEA, its analysis capabilities, its post-processing features, pre-processing features, and how we can model a geometry very easily in Midas FEA. Towards the end of the webinar, I'll demonstrate before you a model showing linear static analysis of a pre-stressed anchorage block. So let me first go through the overview of Midas FEA. I hope you can see the screens and you can listen to me properly. If you can not listen to me, or if you cannot see the screen which shows the first page of the presentation Midas FEA, please let me know through the chat window. Alright, let's begin. So summing up the analysis capabilities of Midas FEA can do the static analysis, it can do the construction stage analysis. The moving load analysis can be performed, but the moving load codes have not been implemented in Midas FEA, as we have several moving load codes that have been implemented in Midas Civil, but in Midas FEA it's not. We can do the modal analysis, linear buckling analysis, transient frequency response spectrum analysis, material geometry nonlinear analysis, interface nonlinear analysis, the reinforcement or pile analysis. As you know that the soil has an interface with pile, you can create an interface element in Midas FEA and you can perform the interface analysis. The cracking analysis, static explicit contact analysis, the heat transfer analysis, fatigue analysis, and the fluid dynamic analysis can be performed in Midas FEA. So it offers a wide range of analysis types which Midas Civil doesn't. You can do the fatigue analysis and fluid dynamic analysis in Midas FEA, but we cannot perform this type of analysis in Midas Civil, as well as the crack analysis and the interface nonlinearity analysis cannot be performed in Midas Civil, but they can be performed in Midas FEA. So this is again the analysis application areas of Midas FEA. As you can see here, Midas FEA can perform the general detailed finite element analysis, which can be either linear static dynamic analysis of a concrete or a steel bridge. It can perform the buckling analysis of steel structure with material and geometric nonlinearity. The concrete interface and reinforcement nonlinear analysis can also be performed. In Midas Civil, we model the elements. Generally, we model the elements as line elements, but in Midas FEA, we model the elements as solid elements, and then we mesh it, and then we analyze the structure. Again, these are the application areas in which Midas FEA can be used. As far as thermostatic analysis, that is the heat transfer and the heat of hydration analysis is concerned. Midas FEA can perform the analysis of heat of hydration, the detailed analysis of assessment of shear capacity of pavement for the debonding failure, the analysis of thermal effect due to asphalt movement, fire effect on a reinforced concrete slab can also be analyzed. The evaluation of residual stress and integrity of weld part can be analyzed. You can put in the fatigue models, and the fatigue analysis can also be performed, as the crack and fatigue analysis of the surface of structures. The damage estimation of pier, water break, impact by ship can be performed. And apart from that, we have included the fluid dynamic analysis of bridges for the high-rise buildings and tunnels. In Midas Civil or Midas Gen, which is a building engineering software of Midas IT, we can perform the wind loads can be applied to the structures, but we cannot perform the fluid dynamic analysis. Midas FEA provides you the fluid dynamic analysis, and also the semi-coupled fluid structure interaction analysis can be performed. The direct analysis of soil surface interaction can be performed, and apart from that, the high-end analysis such as crash, fatigue as I talked about, and the fracture mechanism can be performed. The screen in front of you shows you the configuration of Midas FEA. Basically, FEA is composed of separate things, such as the first thing is modeling. We model the geometry in Midas FEA, then we generate a mesh, then we perform the analysis. After performing the analysis, the user can go to the post-processing mode and see the results there, or the user can also generate a report with the inbuilt report generator feature of Midas FEA. The framework of Midas FEA is similar to the other Midas IT family programs. We have a main menu, as you can see here, works tree, which tells you about the work that you have done so far in the model. The property window here, toolbars, task pane, etc. So let me take you to Midas FEA now and show the different parts. So as you can see here, this is the main menu bar. Here the works tree is located, and whatever you do here, let's say I want to create a solid. So in the solid, I can see that I have created a solid here. So this becomes a very good functionality to see whatever we have done. Not only the solid or geometry, but the boundary conditions, as you can see here, the loads can also be seen. As I talked before, this would be the demonstration example which I will show you towards the end of the webinar. I'll do the linear static analysis of a PSC anchorage block. So now let's first talk about the geometry modeling in FEA. Since the modeling of the geometry is the first thing that the user has to do, Midas FEA has provided users a lot of features that makes the modeling very easy. As you can see here, if you have a face, you can extrude it to a solid. You can also extrude a solid or a shell through a guide curve. As you can see here, if I sweep it, it becomes like this. So if the bridge is curved, this functionality becomes very easy. Also, we have a revolve feature with the help of which you can revolve a profile. And for the generation of the tapered sections, we have a function known as loft. Here you define different sections along the different portions of the bridge, and using the loft function you can create the geometry, as you can see here. Again, advanced geometric modeling features are available, such as trim surfaces. As you can see here, I made certain geometries like cylinders here, and I trimmed them so as to make them one. So as you can see here, this is the main cylinder here, and I have joined certain cylinders with him, and after trimming it, they become a unit. And you can also use the offset commands to create an offset, or the chamfer or fillet can be used. Now let me take you to Midas FEA and show these geometry features there. So let's say these are the two solids that I have. And now I want to create a cavity in this bigger sphere because of this rectangular box. So I can use the Boolean operation such as cut, copy, fuse. If I select fuse, I can select both the solids and fuse them into one. So after fusing, as you can see, it has become a single solid. And if I see the solids here, there is a single solid only here. Now let's go back. Now you can see there are two solids here, and if I apply a Boolean operation cut, so as you can see here, I cut the rectangular portion from the sphere. Now I will show you the sweep feature of Midas FEA. Let's say this is a section that I'm going to use for the bridge, and my bridge profile is curved like this. So what I'll do, I will go to geometry, generator feature, and sweep, and I'll select the profile which I want to sweep. The guide curve will be my line, which I have already defined as a curved line, as you can see here. And if I sweep it, as you can see here, I have created the curved bridge. But I want to create the ducts inside. So what I'll do, I'll use the sweep command again. So basically I'm making 3 more solids so that I can use the Boolean function to cut them from the main solid. So now I have 4 solids, as you can see here. So I'll use the Boolean So as you can see here, I have 4 solids. And I'll select the Boolean operation cut, and I'll cut all the other solids from the main solid. So now you can see that I have generated the desired section of the bridge very easily by using the sweep and the Boolean functions together. After we generate the solid geometry, we need to mesh it. In Midas Civil, we have a variety of automatic mesh generation features available. The user can directly generate a mesh out of a solid geometry, or he can also mesh the plated surfaces. As you can see here, the 2D meshes, the one-dimensional mesh, and the solid meshes can be generated. With the help of automatic surface meshing, Midas FEA does the automatic meshing and it determines the element size wherever required. But the user can provide its own element size for the meshing. As you can see here, apart from the automatic meshing, the user can also use the map meshing feature, which is a structured mesh and is used sometimes to get the correct results. Sometimes the structured mesh is favored over the hexagonal or the triangular mesh. Now I'll take you to Midas FE again and I'll show you how we can automatically generate the mesh in Midas FEA. So this is a solid that I generated. Now if I want to mesh it, I can use the size control. With the help of size control, I can control the size of the mesh along an edge. So let's say I want the number of divisions for meshing for this edge as to be 4. So as you can see here, this edge will be divided into 4 different parts for the generation of the mesh. Also, the mesh control can be applied to the solids and on the surfaces. After that, we can either do the auto mesh or the map mesh, which is a structured mesh. So let's do the auto mesh, the solid auto mesh of this. Here you can preview it before you mesh it. So as you can see here, this line will always be divided into 4 different parts, whether I select whatever element size I select here. So Midas FEA has automatically determined the appropriate mesh size, and since I have defined a mesh number of divisions for this edge, so it follows the rule defined by the user. After that, the user can also check whether the mesh is appropriate or not. The free faces can be checked. As you can see here, the free faces implies that there is no connectivity to the mesh after that. So that means the free faces should always appear only at the outermost surface of the element. So as you can see here, if I hide the solid, so as you can see here, there is no orange line that is inside the structure. That means the mesh generated is proper and the analysis results will be correct. After the mesh generation, the user needs to define the interface elements. As you can see here, this is a composite section having a steel beam inside the concrete. So we need to provide an interface element between the concrete and the steel. We can provide that interface element, as you can see here. Also, the reinforcement can be provided. So the reinforcements can be provided in two ways. We can either embed a bar, which is an incompatible mesh, as you can see here. This bar doesn't lie in the mesh nodes, or you can also apply the reinforcement as a truss, which is a compatible mesh. As you can see here, it's a compatible mesh because the rebar has a node which connects it with this mesh. So there are two ways in which the reinforcement can be provided in the structure in Midas FEA. As far as the elements are concerned, in Midas FEA we can either model the 1D elements such as truss, a gap, hook or cable, or we can model the beams. As far as 2D elements are concerned, we can model the plane stress, plane strain, axis symmetry, plate and shell models. For 3D, we can model the brick, wedge or tetra. For the reinforcement, as I told you just now, the embedded bar or the embedded grid can be used. Now let's talk about the load. In Midas FEA, you can apply the load as a body force, which is the self-weight of the structure. You can apply any factor to that self-weight, or you can apply the force or the moments to any node. And all the typical loads such as the pressure loads, the beam load, the pre-stress load and the temperature loads can be applied to the structure. The heat flux, which is used for the thermal analysis, can be applied. The time forcing function for the times T analysis as well as the thermal stress analysis can be applied. The time varying load can also be applied for the times T analysis. And response spectrum analysis can be done. As far as the boundary conditions are concerned, the user can apply the constraints such as the rotational constraints and the translation constraints. The multi-point constraints can also be applied. In Midas FEA, there is a very prominent feature known as arbitrary loading. With the help of arbitrary loading, you need not to define the load on the specific nodes. As you can see here, I have defined the load as a plain load which doesn't fall on the nodes of the meshed structure. So this is a very useful function of Midas FEA because with the help of this type of loading, we can simulate the load of the tire acting on the bridge. So these are the different analysis type of Midas FEA. The first is the linear static analysis. The linear static analysis implies the simple static analysis as we do in Midas Civil or some of the softwares. The different equation solvers are available such as direct solvers, multi-frontal sparse Gaussian solver and skyline solver are available. And for the iterative solvers, precondition, conjugate, gradient and the generalized minimum residual solvers are available. With the use of these solvers, the analysis time become very less. As you can see here, in model A, we have the plate elements and the number of elements are 30,000 and the number of degrees of freedom are 180,000 and the multi-frontal solver took about 35 seconds to complete. And as you can see here, the comparison of different solvers. Midas FEA can perform the eigenvalue analysis, and the different methodology that Midas FEA can use are the Langko's subspace iteration and the Ritz vector. For the linear buckling analysis, the critical buckling modes can be determined and the load combinations for which the buckling has to be performed can be determined. As far as the dynamic analysis is concerned, the user can perform the direct transient response, the modal transient response. The time-steady analysis can be performed using the time forcing function, and Midas FEA has the database of 54 earthquake acceleration records that happened in the past. The nonlinear analysis can be performed which takes into account the geometry as well as the material nonlinearity. The boundary nonlinear analysis for the dampers, viscous boundary, etc. can be provided. In Midas FEA, you can model the dampers, you can mesh them, and hence you can see the stresses inside the dampers as well as. The frequency response analysis, such as the response spectrum analysis, can be performed, and the different combination methods such as SRSS, CQC, and absolute sum can be used. For the material nonlinear analysis, Midas FEA equips the user with several material models such as von Mises, Tresca, Moore-Column, Drucker-Prager, Rankine, and the user can also supply its own user-defined material. As well as for the nonlinear behaviors, the hardening and the softening behaviors can be supplied in Midas FEA. And the different iteration methods such as the full Newton-Raphson, modified Newton-Raphson, etc. are available for performing the material nonlinear analysis. So as you can see here, this shows how the user can supply the user-supplied materials for the geometry nonlinear analysis or the material nonlinear analysis. Fortran coordinate library can be used. And FEA supports not only the nonlinear elastic but the elastoplastic behaviors of a material. The user-supplied material can be used seamlessly with all elements which allow material nonlinear behaviors. So this is how the user can supply the user-supplied material in the form of Fortran coded library. Again, the geometry nonlinear analysis can be performed using the updated Lagrangian or the total Lagrangian method. And the interface nonlinear analysis, as I told you before, this is a beam containing a steel inside, as you can see here, and we have an interface between the steel and concrete, and we are performing the interface nonlinear analysis. As you can see here, we can define an interface surface and we can assign nonlinear properties to that interface, with the help of which Midas FEA will perform the interface nonlinear analysis. So if a slip occurs between the concrete and steel, Midas FEA can tell you exactly where the slip has occurred and what is the value. The reinforcement analysis can be performed. As I told you before, the embedded and the truss or interface elements can be used. And Midas FEA provides you the detailed results for the reinforcement. As far as the reinforcements are concerned, the user can use the steel reinforcement or the user can use the tendons for the same. The tendons can be allowed to act as the pre-stressing elements, and the pre-stress can be applied to the structure. In Midas FEA, the pre-stress can be applied not only to the beam elements or the plate elements but also to the solid elements. We can also model the interface property between the tendon and the concrete. As far as the crack analysis are concerned, the different crack analysis models such as total strain check, smeared, and crack index are available, and the user can use any one of these to perform the crack analysis. The crack pattern can be obtained, and as you can see here, this is a crack pattern plot. For the thermal analysis, the heat of hydration analysis can be performed. The viscoelastic models such as Kelvin, Maxwell, creep shrinkage. The creep and shrinkage models for different design codes are available in Midas FEA, and the user can select any one of them and assign it to a material, and the creep and shrinkage properties will be used in accordance with the heat of hydration analysis. And the heat transfer models such as We can perform the steady state, the transient analysis, the conduction, convention, and radiation analysis, and the pipe cooling analysis in Midas FEA. Again, the user can perform the static contact analysis, which can be surface to surface or tight. The different elements that can be used for the static contact analysis, we can use 2D or 3D both. And the geometry nonlinearity and the material nonlinearity behavior can be simulated. As far as the fatigue analysis are concerned, the different methods that are available are SN method, EN method, load stress history, rain flow counting, mean stress corrections, etc. And as you can see here, SN curves of fatigue design codes such as Japanese code and the ASTO codes are available, and the user can directly select the SN curves defined in these codes for the fatigue analysis. That was about the modeling, meshing, and the analysis features available in Midas FEA. Let's talk about the different post-processing features that are available in Midas FEA. As you can see here, Midas FEA provides complete support for visualization and interpretation of results. We have several features such as the contour plots and animations, clipping planes and slice planes, etc. And we'll talk about them in our demonstration. Also the mirror plots, as you can see here, if I have modeled only half part of the solid, I can draw a mirror plot. As you can see here, the diagram plot can be obtained, the vector plot, and the results can be extracted in the form of tables and the MS Excel compatible tables also. On the curve diagrams, which are relatively very important for the plate bridges, can be obtained. And the flying view is available. With the help of flying view, the user can virtually move inside the structure to see whether the stresses are in range or not. So that was a general introduction to Midas FEA, and now let's move on to our demonstration, which is a linear static analysis of PSC anchorage block. Let me open a model. So this is the section that I'm going to use, and I'll apply a pre-stressing force to this section. As you can see here, these are the line models, and first I need to make the solid model out of it. So first I'll use the loft feature of Midas FEA, and I'll create a solid. Now I will use the Boolean operation cut to make the ducts inside the cross section. So as you can see here, the first purpose is complete. I have made duct inside the solid that I will be using for the bridge. Now I have to apply the pre-stressing. For that, I will have to model the pre-stressing blocks first. In Midas FEA, you can import the geometry from the step. As you can see here, we can import either the DXF files, or in the advanced geometry input, we can input the step file, IGES, DXF, ACES, and Parasolid. So now I'm going to import a step file. But before that, I want to move my work plane in such a direction that the step file imported is appropriate. I'll be doing this tutorial very slowly in front of you so that you can understand what's going on. So first I will change the work plane as a global XZ plane. So as you can see here, I have changed the work plane. Now I'll import the step file. So as you can see here on this side, I have imported a step file. Let me hide the solid for better understanding. So this is the step file in black, as you can see. Now I'll make surfaces out of this step file. So I'll use the create surface command. And I'll create certain faces. The idea behind is that I want to extrude the faces to make them into a solid. So first I will make the planes. So as you can see, I have made 5 planes, and now I am ready to extrude these planes to make the concrete blocks for the anchorage. First I will translate these two to a certain position. So as you can see, I have used the translate feature of Midas FEA to translate the plane surfaces. And now I have translated this. I hope that you can understand what am I doing. Right now it would be a quite messy for you, but after some time you'll realize why I have done this. So please give me some time. Now I'll use the extrude command to extrude a face to make into a solid. You can see the preview like this. So this is a solid that I'm going to make from a face. Now I will extrude another solid. And preview it. As you can see here, it's going in the different direction. So I'll use the reverse direction and I'll try to move it in the direction I want. So this is the solid that I have made out of the wires. So the first step was to convert the wires into a face. Then I extruded the face into the solid elements. And half of the work is finished. Now I will extrude the bottom faces to make them into a block. So now I have done what I wanted to do with this imported geometry from the step file. Now let me show you what all do I have. Let me make this thing a bit transparent. So as you can see here, I have a main solid, and inside that main solid I have several concrete blocks. I can apply different transparency to different solid blocks. So as you can see here, I have several blocks inside the concrete, but my desired shape includes a block at the left and the block at the right. So I don't need the middle portion. So to delete the middle portion, I'll create a plane, and after creating a plane, I will clip the solid from that plane. So as you can see here, I will first create a plane. So I've created a plane here, and I'll use the clip solid command to trim the solid. So this is the solid I want to trim, and this is the surface with which I want to trim it, and I will trim it on two different points. So after trimming, I obtained the concrete block at the left and the right position, as you can see here. So the modeling that I wanted to do for the concrete block has been finished. Now I'll open another model in which I have modeled the tendons already. For modeling the tendons, the functions that will be used are exactly same. So just to avoid that mechanical protocols, I would just use another model, and I'll show you what all I have done in that model. So as you can see here, so this is the solids, these are the solids that I used, and I have created a duct hole for the tendon here. And I use the auto mesh command to mesh the solid. So the structure that you can see here is meshed. I have also defined the seat control along various edges, as I told you before, and the seat controls can be seen inside the mesh. So the size control, as you can see, so these are the mesh sheets that I have used. And I can also edit the mesh sheet here, and after editing the mesh sheet, I can mesh it again if desired. Now I want to apply the boundary conditions. So I go to analysis, and I go to boundary condition, and I'll select the constraint. I'll apply the constraint to a surface. So I selected the surface, and I'll apply all the degree of transactions to be restricted here in both the sides. So I have applied one restraint in the boundary condition. You can see that the constraints have been applied. And now since this is a part of the solid, which is half of the solid, so I have to apply constraints on this side as well. So I have applied the constraints, and the user can see what all constraints can be applied here. So as you can see here, these are the different constraints that I have applied. After that, I want to apply some loads. So I'll go to analysis, load, and I'll apply a body force, which is a self-weight of the structure. And now I'll apply a pre-stress force in the form of a pressure. Since this is the analysis of a concrete anchorage block, I don't need to model the tendons. So instead of tendons, I have modeled the anchorage block here like this. And now I'll apply a pressure load on this. So I use a phase pressure command, and I am selecting the surface, and I'll apply a load of, let's say, this much kilonewton. So I applied the load, and now I'll apply the load on the other side of the block, which is here. So I again go to analysis, load, pressure loads, and I'll select the surface again, and I click on OK to apply the load. So I have applied the load and the boundary conditions. So the last thing that I'm going to do is define a material. So as you can see here, I have already defined the material, and I can apply the temperature dependent properties such as elastic modulus, Poisson's ratio, and expansion coefficient here. The structural properties that will be used for the linear static analysis are these. And after that, I need to define a property. And the properties can be defined as 1D, 2D, 3D interface, reinforcement, and others. So I'll define a 3D interface property. So I have assigned the material and the material coordinate system to the element property. And now I'm ready to analyze this model. So I'll open another analyzed model to show you the results. So in the postwards command, you can see the reactions. So these are the reactions here. You can see the displacements, and you can go to the post, extract result, or the probe result. With the help of probe result, you can get the value of the result. As you can see here, the tag appears which shows the value. Also, you can see the 3D stress diagrams here, and you can use a clipping plane as I talked about. Here I can define a clipping plane as you can see, and I can move it wherever I want. So if I want to see the stresses here, the clipping plane clips the solid, and it shows me the stresses wherever I want. So if I want to see in the y direction, I'll use this, and here you can see I have clipped it. I can hide the mesh. As you can see, the mesh edge can be hidden. So this is how the clipping plane works. Again, I can define another clipping plane. Let's say here, and you can see what are the stresses. you can generate tables. Just right click and click on table to generate the tables, and select the elements for which you want to create the table, and the tables will be created for the stresses. So that was about the example, the demonstration I showed you. I gave more stress on the modeling and how to model the pre-stressed concrete anchorage block in FEA. I tried to use many geometry features so that you have a general idea about how Midas FEA can be used for the detailed analysis of concrete bridges or buildings. So that leads to the end of the webinar. And if you have any questions now, then you can ask me the questions through the chat window. Now there is a question from Lydia. He wants to ask, after I extruded a face, for example, can you change the distance extruded? Well, Mr. Lydia, we cannot change the extruded distance, but what we can do, we can change the coordinates of the nodes. So if I talk about the geometry, but that would be too complex. So if you have extruded a plane to a solid, then it is not possible to revert it back. So if, let's say, the extrusion distance was 10 meters and you want to make it 8 meters now, so the best way is to extrude it again by just deleting the solid. If you have any more questions, you can ask me. One more thing, the user can apply the analysis control as 3D or 2D XY plane, as you can see here. There's another question by Mr. Stanley. He wants to ask, can Midas FEA be used for mechanical design? Mr. Stanley, can you be a bit more specific about what type of design are we talking about here? If you're talking about the analysis for heat transfer and something like that, which the mechanical engineers usually do, then yes, Midas FEA can be used for that. But if I don't really understand what type of design you're talking about here, but yes, Midas FEA can be used for the mechanical structure analysis. Midas FEA has been used to analyze several structures such as the FEA analysis on the aeroplanes, the analysis of door locks, etc. have been done on Midas FEA so far. Okay, so like design a bike, I hope you're saying that if you model a bike inside, yes, you can do that. And for details about this, I would like you to send me an email at esupport@midasit.com, and for the detailed description for this kind of question, like the mechanical analysis, I will let you know through an email. There is another question by Mr. Oleg Tele. He wants to ask, I want to know how to apply the creep and shrinkage to the structure. So if you go to the material properties here and you create a material property, so here you can apply the creep and shrinkage time dependent behavior. So you can select the creep and shrinkage time dependent behavior and you can apply it to the material. So in this way, the structure will respond to the creep time dependent material properties for creep and shrinkage and the compressive strength. I hope it answers your question, Mr. Oladile. If you have any more questions, you can ask me right now and I'll be more than happy to answer any of your queries right now. Or if you have further queries after the webinar, you can send me the queries at esupport, E as in England, support at midasit.com. So I hope the webinar session was fruitful to you in terms of understanding Midas FEA. If you have any questions after this webinar, if you go through the recording, if you want the recording, we can send you the recordings but if you want the recording, please send me an email at esupport@midasit.com, or you can send an email at info@midasit.com too, and we'll send you the recordings. And if you have any more questions after the recording, you can just send me an email and I'll be more than happy to answer any of your queries. So thank you very much for attending the webinar, and I hope you have a great day ahead. Thank you very much.